Hey y'all, today we're going to be talking about extrema of functions of two variables. Now just like in our original study of derivatives, we wanted to find where maxima and minima occurred at. This proved useful in the business world when we wanted to minimize cost and maximize profit. Well, now that we've opened up our eyes to a new class of functions, functions of two or more variables, we want to find the maxima and minima of it. So, without further ado, let's dive in. Now in order to talk about how to find extrema, it would be helpful to know what we mean by extrema. So a function f of x comma y has a relative max at a point x naught comma y naught if it is the largest value out of any points close to it. Said mathematically, if we have a relative max here, that means that f of x naught comma y naught is greater than or equal to any other f of x comma y for x comma y close to x naught comma y naught. Now we have a minimum at x naught comma y naught if it's the smallest point compared to all the points around it. Now what that means mathematically is f of x naught comma y naught is less than or equal to f of x comma y for any x comma y close to x naught comma y naught. So the largest point in the neighborhood of it versus the smallest point in the neighborhood of it. That's what we mean by max and min. Graphically speaking, we can see that this point at the top of our cup will actually be a maximum. Now it's bigger than any points around it. Same over here, except for now we're at the bottom, so that would mean a relative min. Now there are notions of absolute max and absolute min, where you are the biggest and the smallest point everywhere globally. However, what we're talking about is relative max and min. So you are allowed to be bigger than this at some point. A relative max just means a point that's bigger than anything close to it. So think like a peak. Versus over here, a min just means something smaller than anything close to it. So think yet again, a valley. Now that we know what relative extrema actually are, how they're defined and what they look like on a graph, let's make an attempt as to how to find them. As with anything, let's base our guess on how we treated the first derivative of a function of one variable. With a function of one variable, we set the derivative equal to 0, giving us our critical points, and those were usually pretty good guesses as to where the relative extrema are. So, maybe a first guess, given a function f of x comma y, would be to take our first derivatives, which we have two, f of x and f of y, and require them both to be 0. This seems like a pretty good guess. Now let's dive into it further in the upcoming slides.
Now you can see in this first picture that we have a perfectly good relative maximum. And if you notice, right at the relative maximum, both tangent lines in the x and y direction will be perfectly flat. Therefore, it makes sense that f sub x and f sub y at this point are both equal to 0. Moving on to a relative minimum, you'd see the exact same thing. Both f sub x and f sub y are equal to 0. So we might ask, what's the problem with just solving for where f sub x and f sub y equal 0 to get our maxima and minima? Well, the issue is saddle points. If you look at this saddle point, named because it looks like a horse's saddle, you can see that both the rate of change in the x and y direction at that point will also be 0, meaning that f sub x and f sub y equals 0 at that point. So now our task will be distinguishing between maxima, minima, and saddle points.
Now that we've seen the issue with just saying the first partial derivative is equal to 0, the issue being potential saddle points, we need a way to distinguish between maxes, mins, saddle points, and potentially nothing. This is the way we're going to do it. This is called the second partials test, otherwise known as the d-test. And, just like the title says, this will actually be similar to our second derivative test for functions of one variable. Let's dive into it. Let f of x comma y have continuous second partial derivatives. To find the relative extrema, we'll do the following process, which by the way, you will be given a formula sheet for on the final. Step 1. Find f sub x, f sub y, so your first partial derivatives, as well as f sub xx, f sub xy, and f sub yy. Notice I did not say find f sub yx. The reason for that is we're going to be working with functions where f sub yx is equal to f sub xy. As a second step, what we're going to do is solve a system of equations f sub x equals 0 and f sub y equals 0. This really is solving for a point where both first order partials equal 0, giving us potential maxes and mins as well as potential saddle points. Let's let a comma b be a solution to this system of equations. Taking a comma b, we'll plug it into the function d. So third step, evaluate d of a comma b. What this will be is a comma b plugged into f sub xx, whatever number that is, times a comma b plugged into f sub yy, minus a comma b plugged into f sub xy squared. We'll have three numbers, number 1, number 2, number 3, in which you'll actually get a number for your solution to this. Step 4, once we have all of this information, is to interpret your results. If d, your value you got from step 3, is positive, then we're getting somewhere. If d is positive and f sub xx with a comma b plugged in, this thing right here is positive as well, we will have a minimum. Positive d, positive f sub xx, minimum. If we have a positive d and a negative f sub xx, we will have a max. This is where you're similar to the second derivative test for functions of one variable. F sub xx being positive kind of reminds us of being concave up in the x direction. Concave up led to a minimum. Similarly, f sub xx being negative kind of reminds us of being concave down. Well, that was in turn a max. These two tests are pretty similar. Now what happens if your d is negative? If your d is negative, you don't have to look at any second derivatives. If your d is negative, you can just say, hey, we have a saddle point. Last but not least, just like the second derivative test for functions of one variable, if this guy equals 0, it turns out this test gives us no information, and we would have to rely on another method. As for this class, turns out this test will always work. Now, let's dive into some examples where we work through this process, which yet again, you'll be given this whole thing as a final, or as a formula on the final. As a first example, let's find the relative extrema of the function f of x comma y equals negative 3x squared minus 4y squared minus 6x minus 2y plus 9. My 9s sometimes look like A's, let's tighten that up. In order to do this, we'll rely on the d-test, or the second partials test. Now, the first step of that was to find all of our partial derivatives, basically. So first off, let's find our first order partial derivatives. F sub x means you hold y constant and only derive the x terms. We'll get a negative 6x from here. There's no x present, so we get a 0. Minus 6 from here. And then no x is present in the last two terms, so that's what we arrive on. F sub y will be, well, no y here, so we get a 0. Nor any y's here or here, so the only two terms we have to derive are this. Giving me a negative 8y from here, minus 2. Now, let's find our second order partials. And remember, we only have to find 3 of them. F sub xx, deriving f sub x with respect to x, gives me a negative 6. F sub yy, also easy, deriving this with respect to y, gives me a negative 8. And then last but not least, f sub xy, deriving this guy with respect to y, well, since there are no y's present, that gives me a 0. Second step, draw a little barricade, was to solve the system of equations f sub x equals 0 and f sub y equals 0. That system of equations. Well, now that we have what f sub x and f sub y are, let's plug those in. So this is really just negative 6x minus 6 equals 0, and negative 8y minus 2 equals 0 as well. Well, if we take the top equation, add the 6 over, and divide by negative 6, what we'll get is x is equal to negative 1. We can do a similar process on the bottom, add the 2 over, so we'll get negative 8y equals positive 2, and divide by negative 8, we'll get y is equal to negative 1/4. Now, when we looked at our test, we said, hey, let a comma b be a solution. Well, our solution to this system of equations is the point negative 1 comma negative 1/4. That's our potential relative max or relative min, or potential saddle point. The way we find out is through our third step, evaluating d of a comma b, or in this case, d of negative 1 comma negative 1/4. Now remember what that equaled. That thing was f sub xx of negative 1 comma negative 1/4 times f sub yy of negative 1 comma negative 1/4 minus f sub xy of negative 1 comma negative 1/4, with that last term being squared. Well, if we look what these guys are, if I plug in negative 1 comma negative 1/4 into f sub xx, well, there's no spot to plug it in, we just get negative 6. F sub yy of negative 1 comma negative 1/4, plugging in that point to here, just gives me negative 8. And last but not least, plugging in negative 1 comma negative 1/4 to f sub xy is just 0. Ultimately giving me as an answer positive 48. And yes, sometimes plugging in your point, your solution to this system of equations, into these second partial derivatives really is that easy, because sometimes these just end up being constants. Now ultimately, step 4 said to interpret your answer. The first thing we look at is, what is d? Is it positive, negative, or equal to 0? In this case, d is positive. Our 48 is definitely positive. Since d was positive, we resorted back to f sub xx. So d is positive, and f sub xx, being negative 6, is negative. Those two bits of information combine to give us that negative 1 comma negative 1/4 leads to a relative max. And that right there is your answer. So yet again, you'll be given this process on a formula sheet. In particular, you'll be given this part, your interpretation, on a formula sheet. But it helps to remember d being positive leads to either a max or a min, and then just evaluate the second derivative, just like the first are functions of one variable. We had concave down right here, which led to a max. Let's dive into a more complex example. Now let's find the relative extrema of the function negative 5x squared plus 4xy minus y squared plus 16x plus 10. Yet again, we're going to lean on the second derivative test, the second partial test, or the d test. First step in all of those is going to be to find your first order partials as well as 3 of your second order partials. F sub x, deriving everything with respect to x and holding y constant, gives me negative 10x from this term, plus 4y from this term right here. This term goes away, there's no x present, plus 16, and that term goes away as we have no x present. F sub y, deriving this with respect to y, gives me a 0 in this spot, no y present, plus 4x minus 2y And then yet again, no y's elsewhere, so that is f sub y. From here, we solve for f sub xx. Deriving this guy with respect to x just gives me negative 10. F sub yy. Deriving this guy with respect to y just gives me negative 2. And last but not least, f sub xy. Deriving this with respect to y gives me positive 4. And now, like I said, we don't care about f sub yx. We'll be working with functions where that is actually equal to f sub xy. If we derive this with respect to x, we see that we also get 4. Now that was step 1, get your hands on all of this. Step 2 was solve the system of equations f sub x equals 0 and f sub y equals 0. Now this is where we're going to have to do a little bit of pre-calculus, because this system of equations, if I plug in, will be negative 10x plus 4y plus 16 equals 0, and 4x minus 2y equals 0. Now, this is probably better written, if I may, by moving this 16 over, giving me negative 10x plus 4y equals negative 16. And then the bottom remains the same, of 4x minus 2y equals 0. Like I said, here's where you do some pre-calculus. Either solving this system of equations, these two right here, by either substitution or elimination. As elimination seems easy, since the y's are very close, I'm going to do it that way. But feel free to solve it via substitution. If I time this whole thing by 2 on each side, what I'll end up with is the system of equations, negative 10x plus 4y equals negative 16. I didn't touch the top one. And then the second line, now that I'm multiplying everything by 2, becomes 8x minus 4y equals 0. 0 times 2 is definitely still 0. Now the reason that's nice is if I just add these two equations together, kind of adding straight down, we'll end up getting negative 10x plus 8x gives me negative 2x. Positive 4y plus negative 4y gives me 0y, so the y's get eliminated, equals negative 16 plus 0, or negative 16. This ultimately gives me x equals 8. Now that we have x, we need to get our hands on y. The way we do that is by plugging in x to your favorite one of these equations. I'm going to plug in x equals 8 into this equation in order to solve for y. So therefore, since x equals 8, I have that 4 times 8 minus 2 times y still better equals 0. It's starting to look like a football play up here. Now we can just solve that out regularly. 32 minus 2y equals 0. Adding the 2y over gives me 2y equals positive 32. So I just flip them around on the equality sign. Or ultimately, dividing by 2, y equals 16. Therefore, step number 2 results in the point 8, 16 being a potential max, min, or saddle point. 8, 16 is a solution that we will test in our D function. Now because I ran out of whiteboard, I went ahead and copied the relevant information from steps 1 and steps 2 on the whiteboard. Now this wasn't all of it, as we had to do f sub x and f sub y in order to get step 2, but this will be the stuff we need for step 3 and beyond. Now what was step 3? Step 3 said to evaluate the function d of 8, 16. Now remember, this function was f sub xx with your point plugged in times f sub y with your point plugged in minus f sub xy with your point plugged in. And we actually are going to square that last number. Well, if we plug in 8, 16 to f sub xx, oh no, we're getting a bunch of constants again. I shouldn't be saying oh no, that's really a good thing. It makes our life easy. F sub xx of 8, 16 is just negative 10. Meanwhile, f sub yy, being just another constant function, will be negative 2. Minus, ultimately, f sub xy with 8, 16 plugged in, which will be 4 squared. This gives us, upon evaluation, 20 minus 16, or positive 4, for an answer to what d is actually equal to. From here, we interpret our results. So step 4, first and foremost, see if d is positive, negative, or equal to 0. D is positive. As d is positive, we now look to f sub xx. F sub xx in this case is negative. Negative 10. As d is positive, f sub xx will give us whether we are a max or a min. F sub xx being negative correlates to being concave down in the x direction, and therefore concave down leads to a max. Eight, 16 will lead to a relative max. Let's go ahead and look to one more complex example before we go ahead and send you off to the homework. Let's end on a bang with this function. Find the relative extrema of the function f of x comma y equals negative 4 times the quantity x squared plus y squared plus 81, all raised to the 1/4 power. Yet again, we'll rely on the d-test. First step, get your hands on the first order partials as well as 3 of the second order partials. F sub x in this case. Notice we have some stuff trapped by a power. That calls for chain rule. So, we don't shy away from it. Chain rule, remember, is the derivative of the outside times the derivative of the inside, where we're deriving with respect to x in this case. So, the derivative of the outside would be 1/4 times the whole inside, x squared plus y squared plus 81, all raised to the negative 3/4. Subtract 1 from the power. That's the derivative of the outside times the derivative of the inside. As we're just deriving with respect to x, and the only term with x in it is x squared, the derivative of the inside is just 2x. Now notice that upon simplification, and simplification helps, we'll get the 4's canceling, giving me negative 2x divided by this guy. X squared plus y squared plus 81 all to the 3/4 power. Now f sub y can be found similarly. Or excuse me, f sub y. Now f sub y is just going to be, yet again, a chain rule, so the derivative of the outside, which is the same, it'll be 1/4 x squared plus y squared plus 81 raised to the negative 3/4, the derivative of the outside, times the derivative of the inside. The only term with y on the inside is y squared. Therefore, the derivative of the inside with respect to y is just 2y. Ultimately giving me f sub y equals, as the 4's cancel, negative 2y all over x squared plus y squared plus 81 to the 3/4 power. Now, what we go ahead and do is find f sub xx, f sub xy, and f sub yx. f sub x. Now what I'm going to go ahead and recommend is actually not doing it this way. I wrote it like this for a later purpose. What I'm going to recommend is deriving instead negative 2x times x squared plus y squared plus 81 all to the negative 3/4. The reason I recommend this is right here we have a quotient rule as well as a chain rule when deriving the bottom. So may as well make it a product rule times the chain rule. Therefore, when we derive this, we have a product rule. That will be first negative 2x times d second. Do yet again another chain rule. Derivative of the outside is negative 3/4 x squared plus y squared plus 81, and then subtracting 1 from the power gives me a negative 7/4 times the derivative of the inside with respect to x, which is yet again 2x. First, d second, plus second, which we have x squared plus y squared plus 81 to the negative 3/4, all times d first, negative 2. And yes, this is pretty nasty. Well, what we go ahead and get, if we do f sub y, would be something very similar. Yet again, we'll bring this to the top to make ourselves have a product chain rule, so negative 2y times x squared plus y squared plus 81 to the 3/4. And upon doing the product chain rule, we'll get first negative 2y times d second, so that's the chain rule yet again, giving me a negative 3/4 x squared plus y squared plus 81 to the negative 7/4 times the derivative of the inside, which is 2y. So derivative of the outside times the derivative of the inside while deriving the second term. So we have first d second plus second x squared plus y squared plus 81 to the negative 3/4 times d first, which is just negative 2. And now last but not least, f sub x comma y, or f sub xy, excuse me, deriving this guy with respect to y will actually be a little easier. The reason for it is we have negative 2x out front. Since I'm deriving this thing with respect to y, that is no better than a constant. So I just copy it down. Negative 2x. Now, in order to derive this with respect to y, I still need a chain rule though. But we just don't have the product rule now. So negative 2x times the chain rule of this guy, negative 3/4. Let's go ahead and make this a bracket. So deriving the outside gives me negative 3/4 x squared plus y squared plus 81 to the negative 7/4, the derivative of the outside of this, times the derivative of the inside, which as we're deriving with respect to y, gives me positive 2y. Now, I strongly advise you to go ahead and go slowly through this. And by the way, there is some simplification we can do here, in which we'll see on the next slide. But really work this out yourself and try to grasp this. I know it looks nasty, but the steps to come won't be so bad. I promise. Now, as you can see, I went ahead and moved f sub x and f sub y in the form that we're going to use them up over here to give me more room to simplify these guys out. The reason we want to simplify them out is eventually we're going to be plugging in our solution over into these guys. So let's start with f sub xx. What can be simplified here? Well, the immediate thing that comes to mind is, how about this 2x times this negative 2x? That should give me a negative 4x squared. But the 2 and the 2 will cancel with that 4 down here. The negative 3 survives, giving me, well, we'll have positive 3x squared. And that comes from combining this with this with this. So positive 3x squared times what was left over, x squared plus y squared plus 81, all to the negative 7/4 power. Now we still have the second term, so we'll still have minus 2, just moving the negative 2 to the front, x squared plus y squared plus 81, all to the negative 3/4 power. If we want to, we could even go a step further and factor out a negative 7/4 power, as there's nothing really else in common. These two guys are in common though. If I factor out a negative 7/4 power, what we'll be left with is a 3x squared right here, minus 2, and then we have to determine what we gain from this, what we got left over from it. And it turns out it's pretty nice. We're left over with x squared plus y squared plus 81 to the 1 power. The way you can see this is if I multiply back in by negative 7/4, I better get negative 3/4. So another way to do this in your head to figure out what power goes up here is to add the power that you're factoring out, the positive version of it, to this guy. So negative 3/4 plus 7/4 gives me 10/4, which, does not give me 10/4. That'll end up giving me 4/4, which is just 1. So we do get this. In a very similar manner, f sub y, first after noticing that the 2's will cancel with the 4 and the negatives will cancel, will give me our positive 3y squared times x squared plus y squared plus 81 to the negative 7/4. So kind of similar, just a y right here. Minus 2 x squared plus y squared plus 81 to the negative 3/4. I'll go ahead and box this so it doesn't get too confusing. Well, any more confusing than it needs to be. Which ultimately, after factoring out a negative 7/4 power of this quantity, will give me x squared plus y squared plus 81 to the negative 7/4 times what was left over, 3y squared minus 2 times x squared plus y squared plus 81. Now the only thing that we can really simplify for f sub x comma y, I'll go ahead and yet again box this in green. This is the one we will be using. Well, if we look over here, the only thing that really simplifies is kind of this red steps that we've been doing over here. So what do I mean by that? Negative 2 times 2 gives me negative 4, but we're dividing by negative 4. Leaving me with just 3y times x squared plus y squared plus 81, all to the negative 7/4. Now, as horrible as it was, I promise that we're all downhill from here. Step 1 is summarized in this green box, and it's quite a bit. You know, these second partials can be nasty, and indeed they were in this problem. But don't let that scare you. We run towards these problems, not away from them. Step 2. Go ahead and solve the system of equations f sub x equals 0 and f sub y equals 0. You'll be pleasantly surprised with this one. The reason I wanted to write these in terms of fractions, so if I go ahead and plug those in, that's the same as solving negative 2x over x squared plus y squared plus 81 to the 3/4 power equals 0, and negative 2y, if I can write this one a little further down, negative 2y over x squared plus y squared plus 81 to the positive 3/4 power equals 0. Notice that in both cases I have a fraction equal to 0. Whenever you have a fraction equal to 0, that is equivalent to solving when the top equals 0. And all of a sudden this beast comes down to this simple algebra problem, which gives you x equals 0. In a similar manner, we have a fraction equal to 0. Therefore, this only occurs when the top equals 0. And the beast is humbled. Solve this out, we get y equals 0, leading step 2 to say that the 0, comma 0, x equals 0, y equals 0, is a solution. Zero comma 0 is the thing that comes from step 2. Now that we've found all of this information in the green in step 1, and in step 2 we found that 0 comma 0 was a solution to our f of x equals 0 and f sub y equals 0, what we need to do now is evaluate, for step 3, d of 0 comma 0, the solution from step 2. Now this is where you'll actually have to plug in to your second partials. Because remember, this is f sub x of 0 comma 0 times f sub y of 0 comma 0 minus f sub xy of 0 comma 0, with this last term being squared. Now, let's talk about f sub x of 0 comma 0. Notice that a lot of things will cancel. So, if I can do my work over here, f sub x of 0 comma 0 is just 81 to the negative 7/4, because we'll have 0, 0, just leaves with the 81, times 0, 3 times 0 squared is 0, minus 2 times 81. And I know you have a calculator for this. I'm going ahead and showing the work based on if you didn't. Really what this can be then written as is 81 to the negative 7/4 times 81 times negative 2. The reason I write it that way is since we have a common base down here, you can view 81 as 81 to the first power. What you do to simplify that is add the powers together. Negative 7/4 plus 1 gives me 81 to the negative 3/4, all times negative 2. You can go ahead and move that to the bottom, giving you negative 2 divided by 81 to the 3/4. Then remember now that you can go ahead and either raise this to the power of 3 or fourth root it, whichever order you prefer. If you fourth root this first, you'll get negative 2 divided by 3 cubed, which 3 cubed, 3 times 3 times 3, is just 27, giving me that f sub x of 0 comma 0, plugging this in right here, simplifies all the way to negative 2 over 27. Now, f sub y being entirely similar to f sub x, take away this term right here, where it's x versus y. Well, since x and y are both 0, you'll also get negative 2 over 27 as f sub y. Now, last but not least, what is f sub x comma y of 0 comma 0? Well, notice if I plug in 0 comma 0, I'll have 0 times 81 to the negative 7/4, but this 0 right here will eliminate everything, giving me just a 0 in place of this. What this will ultimately be then is 4 over 27 squared, which, if we go ahead and do that, I have it worked out behind you, is 4 over 729. Sorry, I had to look behind. Calculator's back there. Therefore, d of 0, 0 is 4 divided by 729. Now that we've went ahead and solved out d of 0, 0, we go ahead and move on to our fourth step, which is to interpret the results. First thing you look at is your d function. Is it positive, negative, or equal to 0? In this case, 4 over 729, definitely positive. Now that you're positive, since you're positive, you look at f sub xx of 0, 0. In this case, and to be more formal, I should be putting 0, 0 in, so I'll go ahead and adjust it up here as well. In this case, we had a negative number. Negative 2 over 27, which is less than 0. Ultimately, as d was greater than 0, this told me, okay, you're either a relative max or a relative min, leading us to interpret f sub xx being negative, concave down. That means that 0, 0 leads to a max, a relative max, I should say. And that ultimately, and this one was well earned, gives us our answer, and that is our final answer. So, sometimes these derivatives will be nasty, but it is up to us to persevere through it, stick to the process, and hopefully, just like step 2 wasn't so bad, we will have some light at the end of the tunnel. Hey y'all, thanks for tuning in today as we explore the concept of relative extrema of functions of two variables. Now, to start off with the obvious, for a recap, relative maxes and mins are still relevant. We still care about minimizing cost and maximizing profit. So, we would like to find ways to find these maxes and mins for functions of several variables. Why not start with functions of two variables? Now, in order to do this, we couldn't just set f sub x and f sub y equal to 0. It wasn't completely like solving functions of one variable. Instead, we had to adhere to the d-test. Find your partial derivatives, solve the system of equations f sub x equals 0 and f sub y equals 0, evaluate your solution into that d function, and ultimately interpret your results. This was similar to the second derivative test for functions of one variables, but we had a little bit longer of a process, which was a little bit more intensive. So, with that being said, you will be given this process on the final and on your test, but go ahead and try the homework, try to internalize it as best as you can. As always, email me with any questions, and hope you have a great day.